The Atterberg limits are a basic measure of the critical water contents of a fine-grained soil, such as its shrinkage limit, plastic limit, and liquid limit. As a dry, clayey soil takes on increasing amounts of water, it undergoes dramatic and distinct changes in behavior and consistency. Depending on the water content of the soil, it may appear in four states: solid, semi-solid, plastic and liquid. In each state, the consistency and behavior of a soil is different and consequently so are its engineering properties. Thus, the boundary between each state can be defined based on a change in the soil's behavior. The Atterberg limits can be used to distinguish between silt and clay, and it can distinguish between different types of silts and clays. These limits were created by Albert Atterberg, a Swedish chemist. They were later refined by Arthur Casagrande. These distinctions in soil are used in assessing the soils that are to have structures built on. Soils when wet retain water and some expand in volume. The amount of expansion is related to the ability of the soil to take in water and its structural makeup. These tests are mainly used on clayey or silty soils since these are the soils that expand and shrink due to moisture content. Clays and silts react with the water and thus change sizes and have varying shear strengths. Thus these tests are used widely in the preliminary stages of designing any structure to ensure that the soil will have the correct amount of shear strength and not too much change in volume as it expands and shrinks with different moisture contents. As a hard, rigid solid in the dry state, soil becomes a crumbly semi-solid when a certain moisture content, termed the shrinkage limit, is reached. If it is an expansive soil, this soil will also begin to swell in volume as this moisture content is exceeded. Increasing the water content beyond the soil's plastic limit will transform it into a malleable, plastic mass, which causes additional swelling. The soil will remain in this plastic state until its liquid limit is exceeded, which causes it to transform into a viscous liquid that flows when jarred. Laboratory tests, shrinkage limit. The shrinkage limit is the water content where further loss of moisture will not result in any more volume reduction. The test to determine the shrinkage limit is ASTM International D4943. The shrinkage limit is much less commonly used than the liquid and plastic limits. It is the minimum water content. Plastic limit. The plastic limit is determined by rolling out a thread of the fine portion of a soil on a flat, non-porous surface. The procedure is defined in ASTM Standard D4318. If the soil is plastic, this thread will retain its shape down to a very narrow diameter. The sample can then be remolded and the test repeated. As the moisture content falls due to evaporation, the thread will begin to break apart at larger diameters. The plastic limit is defined as the moisture content where the thread breaks apart at a diameter of 3.2 mm. A soil is considered non-plastic if a thread cannot be rolled out down to 3.2 mm at any moisture. Liquid limit. The liquid limit is often conceptually defined as the water content at which the behavior of a clayey soil changes from plastic to liquid. Actually, clayey soil does have a very small shear strength at the liquid limit and the strength decreases as water content increases. The transition from plastic to liquid behavior occurs over a range of water contents. The precise definition of the liquid limit is based on standard test procedures described below. The original liquid limit test of Atterberg's involved mixing a pat of clay in a round-bottomed porcelain bowl of 10 12 cm diameter. A groove was cut through the pat of clay with a spatula, and the bowl was then struck many times against the palm of one hand. Casagrande subsequently standardized the apparatus and the procedures to make the measurement more repeatable. Soil is placed in the metal cup portion of the device and a groove is made down its center with a standardized tool of 13.5 mm width. The cup is repeatedly dropped 10 mm onto a hard rubber base at a rate of 120 blows per minute, during which the groove closes up gradually as a result of the impact. The number of blows for the groove to close is recorded. The moisture content at which it takes 25 drops of the cup to cause the groove to close over a distance of 13.5 mm is defined as the liquid limit. The test is normally run at several moisture contents, and the moisture content which requires 25 blows to close the groove is interpolated from the test results. The liquid limit test is defined by ASTM standard test method D4318. The test method also allows running the test at 1 moisture content where 20 to 30 blows are required to close the groove. Then a correction factor is applied to obtain the liquid limit from the moisture content. The following is when one should record the N in number of blows needed to close this 1/2 inch gap. The materials needed to do a liquid limit test are as follows: Casagrande cup, grooving tool, soil pat before test, soil pat after test. Another method for measuring the liquid limit is the full cone test. It is based on the measurement of penetration into the soil of a standardized cone of specific mass. Although the Casagrande test is widely used across North America, the full cone test is much more prevalent in Europe due to being less dependent on the operator in determining the liquid limit. Importance of liquid limit test. The importance of the liquid limit test is to classify soils. Different soils have varying liquid limits. Also, one must use the plastic limit to determine its plasticity index. Derived limits. The values of these limits are used in a number of ways. There is also a close relationship between the limits and properties of a soil such as compressibility, permeability, and strength. This is thought to be very useful because as limit determination is relatively simple, it is more difficult to determine these other properties. Thus the Atterberg limits are not only used to identify the soil's classification, but it allows for the use of empirical correlations for some other engineering properties. Plasticity index. The plasticity index is a measure of the plasticity of a soil. The plasticity index is the size of the range of water contents where the soil exhibits plastic properties. The PI is the difference between the liquid limit and the plastic limit. Soils with a high PI tend to be clay, those with a lower PI tend to be silt, and those with a PI of 0 tend to have little or no silt or clay. PI and their meanings. 0 to 3, non-plastic, 3 to 15, slightly plastic, 15 to 30, medium plastic, greater than 30, highly plastic. Liquidity index. The liquidity index is used for scaling the natural water content of a soil sample to the limits. It can be calculated as a ratio of difference between natural water content, plastic limit, and liquid limit, Li equals, WPL, / LLPL, where W is the natural water content. Activity. The activity of a soil is the PI divided by the percent of clay-sized particles present. Different types of clays have different specific surface areas which controls how much wetting is required to move a soil from one phase to another, such as across the liquid limit or the plastic limit. From the activity, one can predict the dominant clay type present in a soil sample. High activity signifies large volume change when wetted and large shrinkage when dried. Soils with high activity are very reactive chemically. Normally the activity of clay is between 0.75 and 1.25, and in this range clay is called normal. It is assumed that the plasticity index is approximately equal to the clay fraction. When A is less than 0.75, it is considered inactive. When it is greater than 1.25, it is considered active. Notes. Brief history of Swedish soil mechanics. Retrieved January 15, 2007. A shrinkage limit test. United States Army Corps of Engineers. ASTM D4318-10 standard test methods for liquid limit, plastic limit, and plasticity index of soils. ASTM. 2010. Retrieved February 18, 2011. TRID.trb.org. SOAS. 1979, references, University of Washington lecture notes, Soil Physical Properties, Mechanics, Seed, H.B. Fundamental Aspects of the Atterberg Limits. Journal of Soil Mechanics and Foundations Divide, 92, SM4, retrieved from http, trid.trb.org/ view.aspx ID = 38900, DAS, BM Principles of Geotechnical Engineering. Stamford, Connecticut, Thompson Learning College. SOAS, 1979. Introductory Soil Mechanics and Foundations, Geotechnical Engineering, 4th ed., Macmillan, New York.